Hello friends, subscribers and new viewers of this channel, and welcome to FPGA tutorials. In this tutorial we explain how to generate pulse width modulation signals or PWM signals in Verilog and Vivado. We explain how to precisely control the frequency and the pulse width of the pulse width modulation signals. For that purpose we will use a hardware clock that is provided by our FPGA. Pulse width modulation signals are used for controlling motors, actuators, and other mechatronics devices. Consequently, it is of paramount importance to learn how to generate PWM signals by using FPGAs. In this tutorial, we are using Nexus A7100T FPGA. This is a very popular FPGA that is often used in electrical and computer engineering programs in the US and Europe. However, everything explained in this tutorial can easily be used in the case of other FPGAs. The Verilog code will be the same, the only difference will be in the constraint file and how the clock is attached to the actual ports of the Verilog module. The experimental setup is very simple. Here is the FPGA, and we are using this PMOD port to send the pulse width modulation signal. This blue wire over here is the signal and the black wire is the ground. Over here we are using the breadboard to attach the oscilloscope probes. And here is the oscilloscope probe. Over here you can see the oscilloscope reading, and if I start again the acquisition, you'll see that everything is being acquired in real time. And here is our pulse width modulation signal. Now, after some time over here, you will see the period. The period is 5 microseconds. The frequency of the pulse width modulation signal is 200 kilohertz. And over here, you can see the pulse width. The pulse width is 2.5 microseconds. I have to mention over here that we can precisely control the pulse width of the pulse width modulation signal and the frequency. That is, by properly attaching the clock, we can define a pulse width modulation signal of desired pulse width and frequency that is necessary to control your motor or an actuator. Okay, let's start with explanations and with implementation. The first step is to find the FPGA board specifications and to investigate what types of clocks the FPGA board provides, as well as the clock pin names and numbers. The Nexus A7100T board includes a single 100 MHz crystal oscillator clock connected to pin E3, and this is very important information. This means that the period of the clock is 10 nanoseconds, and in the sequel I will explain how to find this information by looking at the specs of the board. The first thing that you need to do is to find the specs of the board. Consequently, open your favorite search engine and search for your board specs. Over here I type Nexus A7, and then if I scroll all the way down, I can find this official web page. And here it is. Now, if I go all the way down, and if I look inside of this menu, Feature Documents, and if I click on the reference manual, I will find this PDF documents that describes the board. Now, if I go all the way down, if I keep on going down, keep on going down, keep on going down, then somewhere over here, you will find the section 6, Oscillators, Clocks. And over here you can read this: the Nexus 4 DDR board includes a single 100 MHz crystal oscillator connected to pin E3. And this is very important. This is all you need to know in order to attach the clock to your board. So this is the first information. The second information that you need to look at are PMODs. That is, you need to look at how the pins are connected to your board such that you can generate PWM signals. Here is a photograph of the board, and the board has 1, 2, 3, 4, 5 PMOD ports. In this video tutorial we will use this PMOD port over here. This PMOD port is close to this UART connection that's at the same time provides the power and connection to the board from your computer. That is, this is the USB to UART connector. Okay, the next thing that you need to find is the pin diagram. So if you go all the way down to the section 11, let me find it, here it is. Over here you can find this important sketch that explains what are the pins on every PMOD. You can see that these two pins are actually power, and you can see that the power is 3.3 volts. The next two pins are ground, and over here you can see the pins. In this video tutorial, we are going to use this pin over here for the ground and this pin over here to generate pulse width modulation signal. Our PMOD is actually PMOD JD, and this particular pin is H4. Consequently, when we write a constraint file, we need to have information given over here, and we need to know this pin over here, H4. Later on, I will provide an actual wiring diagram. So let's continue with the presentation, and let's explain the wiring diagram. So here it is. Here is our PMOD port. This is the ground wire. The ground wire is attached to this pin, and over here is the signal wire, and this is the pin 4. Okay, now you can attach an oscilloscope in order to visualize pulse width modulation signals. Or another idea over here is to put an LED and to put a resistor, and then you can actually blink an LED by modulating the pulse width of a pulse width modulation signal. So let's continue. Let's start with Vivado and Verilog implementation. Let's start Vivado. Click on Start and search for Vivado. Over here you can see that I'm using Vivado 2024.1. However, you can also use any newer or older version of Vivado. So let's open Vivado and let's wait. Depending on how fast is your system, it might even take a minute to open Vivado. It's a huge program. So let's create a project. Let's click on Next, click on Next, click on Next. And over here you need to find your board. I will click on Boards and I will search for Nexus, and I will click over here. Now, if you don't immediately see your board, you need to click on Refresh. This often happens the first time you start Vivado. Then, another thing that you need to do is to download your board files. You simply need to click here, and then you will see this minus sign. This means that your board is actually installed on the system. So let's click on Next, and let's click on Finish. And here it is. The first step is to define the constraint file. Consequently, click on the constraint, click on plus, click on Add or Create Constraints, then click on Next, then click on Create File, and I will call the file simply as constraint. Then click on OK and click on Finish. And then after some time in this folder over here, you will see your constraint file. So expand this folder and click on the file. Note over here that the extension of the constraints file is XDC. So let's open this file, and over here to save the time, I will simply paste the content. Here it is. And I will explain line by line. First of all, we need to attach the clock to our design. As mentioned previously, the clock is attached to the pin E3. Consequently, we write set property package pin E3, and over here we are relating this pin with this name CLK, which stands for clock. This CLK is actually a port name in the Verilog module that we will declare and define later on. For the time being, just enter this. Okay, the next line actually creates the clock. First of all, we specify the name of the clock. I'm calling the clock simply as sysclock. However, you can also use any other name. And over here, we are specifying the period of the clock. From the manual, that is from the board specifications, we know that the period of the clock is 10. That is 10 nanoseconds. Consequently, over here we need to write 10. Then we need to define the waveform. Consequently, we write dash waveform, and inside of these curly braces, we write 0 and 5. So what is 0? 0 means that the rising edge of the clock starts at 0. That is at the beginning of the clock pulse. Then the fall edge of the clock happens at 5. And this is the meaning of 0 and 5. And again over here we need to type get ports, and we need to refer to the actual port in our module that will be defined later on. Next we need this line. We are here specifying the I/O standard, or the input-output standard. It is LVC MOS 33, and again we need to refer to clock. The next step is to define the pin for generating the pulse width modulation signal and to constrain this pin. Consequently, we type set property package pin H4. So let's look where is H4. This is the H4 over here pin, and this pin will be used to generate pulse width modulation signals. Going back to our constraint file, we need to add this part over here. Again, we need to refer to the port in our module, and the module will be defined later on. The corresponding variable will be called signal. Then again, we need to set the I/O standard. It is LVC MOS 33, and we need to refer to signal. And that's it. Let's continue. In the sequel, we will explain how to define a pulse width modulation signal. For that purpose, it's first very important to understand what are pulse width modulation signals and how they are described. Over here, you can see a basic pulse width modulation signal. First of all, we have two values. We have the low value, which can be 0, for example, and high value, which can be a voltage value specified by the pin of your FPGA. For example, this value over here can be 3.3 volts, can be 1.75, or a similar value. So, initially, we are at low value of voltage. Then we have the rising edge of our pulse width modulation signal. Then we go to the high value. Then this high value is kept constant for the duration of the pulse, or for the pulse width. Then we have the fall edge. We go to the low value. Then the low value is kept from here until the period of our pulse width modulation signal. That is, the period is the duration from here until the next pulse over here. In our implementation, the pulse width will be denoted by pulse length, and the pulse width modulation period will be denoted by the period length. The next quantity that we need to define is the duty cycle. When someone talks about pulse width modulation signals, they will often say, well, I generated a pulse width modulation signal with a frequency of 100 kilohertz and with a duty cycle of 60%. So what is a duty cycle? Duty cycle is simply the ratio of pulse length with period length. That is, in the numerator of a duty cycle expression, you have the pulse length, and in the denominator, you have the period length. In that way, when someone says a duty cycle of 50%, you know that period, or actually pulse length over period, is 0.5. That is, the period is 2 times the pulse length, or the pulse. Before I explain how to define pulse length and period length, I need to mention the following. In our simulations and in our implementation, both the pulse length and the period length will be expressed in the units of the clock cycle, or the units will be the period of the clock cycle. That is, both pulse length and period length will be integers. For example, period length will be 500. So what is unit? Unit is a single clock cycle. To get the period length in actual nanoseconds, you need to multiply the integer value of period length with the period of the clock, and in our case it's 10 nanoseconds. Consequently, 500 multiplying 10 gives you 5000 nanoseconds. The same thing applies to pulse length. The pulse length is expressed as multiple, or it is expressed in periods of clock cycle. Okay, so let's go to Python and let's explain how to define period length and pulse length. For example, we're given a problem to define a pulse width modulation signal with a period of 5000 nanoseconds or the frequency of 2000 Hz and a duty cycle of 50%. Over here you can see the Python code. First of all, I'm importing NumPy. Then over here, I'm defining the FPGA clock period in nanoseconds. As we have seen previously, it's 10 nanoseconds. Then we define the desired period of the PWM signal in nanoseconds. Since we want to generate a pulse width modulation signal whose frequency is 200,000 Hz, we have the period of 1 over this value over here, which gives you 5000 nanoseconds. Then here is the duty cycle, and we need to calculate the pulse width in nanoseconds. We do that by simply multiplying duty cycle pulse width modulation by the period of our pulse width modulation signal. And let's see what do we get. As the result, we get the width of our pulse width modulation signal 2500 nanoseconds, and the period is 5000 nanoseconds. However, to implement the pulse width modulation signal in period in Verilog, we need to express both of these quantities in the units of clock cycles. Consequently, we divide period of the pulse width modulation signal by the period of the clock of our FPGA, and as the result we have period length of 500 clock cycles. The same thing is done with the width of the pulse width modulation signal. We simply take the width, which is 2500, and we divide this width by the period of our clock cycle, and consequently we get the pulse length of over here 250. Good, let's continue. In the sequel, I will present you two approaches for generating a Verilog code that will produce a pulse width modulation signal with the desired frequency and with desired duty cycle. So let's click on Design Sources and click on plus, and click on Add or Create Design Sources, then click on Next, and over here click on Create File. After we click on Create File, we need to give the file name. Let's call our module as main module. And let's click OK, and click on Finish, and click on OK, and click on Yes. Then, after some time, over here in the Design Sources folder, you'll see the main module file. Double click on the file to open it, and over here I will erase everything, and I will paste the content of the file. So here it is. Here's my main module. And let's explain main module line by line. First of all, we are using the time scale of 1 nanosecond. That is, the unit of our implementation is 1 nanosecond. And this is perfectly in accordance with the period over here, units, which are expressed again in nanoseconds. Over here, our main module has two ports. It has the port called clock, and this is the input port, and it has the output port called signal. Now again, if you go back to the constraint file, you will see what is clock. You can see that the clock name is used over here, and in this way, by specifying and using the clock name over here, we are connecting this input port to our actual hardware clock, as you can see from this constraint file. The same thing applies to our signal output port. Over here, the name is signal, and the signal is constrained to the pin H4. That is, when we generate a signal from our module, this signal will be sent to pin H4, and this is very important. Next, over here, on the basis of our Python calculations that are explained previously, we define the period length, it's 500, and the unit is clock cycle. So this will be 500 clock cycles, or 500 positive edges, or the rising edges of our clock. Then over here we have our pulse length. Again, the units are clock cycles, or the period of the clock. And over here we declared an additional variable called counter, and this counter is used to create our pulse width modulation signal. So what's the purpose of the counter? Counter will count from 0 until the period length. And after the period length is reached, we are going to reset the counter. In this way, the counter will iterate through the discrete time steps inside of a single pulse. And the counter is used over here. Over here we use the always statement. And by just analyzing this line, you can see that this block over here is triggered on every positive edge of the clock. That is, on every rising edge of the clock, this block over here is executed or triggered. So let's see what's happening over here. If our counter is smaller than the period length, what do? We simply increment the counter. What does this thing mean? It means that the counter goes from 0, 1, 2, 3, 4, 5, 6, 7, etc. until it reaches 500. When the counter reaches 500, that is when we count 500 positive edges or rising edges of our clock, or 500 clock cycles, what do? We simply reset. That is, we set the counter to 0, and this is how we count. Okay, now we use the counter to simply define over here our pulse width modulation signal. If counter is smaller than the pulse length, then over here we are going to send the high value. Then if this statement is not true, then we are going to send the low value. So let's again take a close look at this statement. Over here you have a condition. This condition can be true or false. For example, if this condition is true, that is, if the counter is smaller than pulse length, we are sending 1 in this bit notation, which is actually 1. Otherwise, if this statement is not correct, we are sending 0 in bit notation, and that's actually low value or 0. And that's it. Simple as that. Nothing special. Let's save this module and let's continue with the next step. The next step is to run the synthesis. Consequently, click over here, then click on OK to run the synthesis, and now you need to be patient. It might even take a minute or two to synthesize this code. Then after some time, this window will pop up, and here it's written that synthesis successfully completed, and then you can click here to run the implementation and then OK. Another way to run the implementation is to simply click over here. However, let's use the first approach. Click here and click OK, and let's click OK. Now the implementation is running, and again, this might take maybe even 30 seconds or even a minute to complete. Consequently, be patient. The next step is to generate the bit stream. You can click here, then OK to generate the bit stream, or you can simply click here to generate the bit stream. So let's follow the first approach. Click here and click OK, and click OK. Again, this whole process might take even 30 seconds. Meanwhile, you can attach your FPGA to your computer by using the USB port. And now you heard this sound. This means that FPGA is connected. And now let's wait until the bit stream is generated. Meanwhile, you can also turn on the oscilloscope. If you have an oscilloscope, you can attach the probes such that you can visualize the pulse width modulation signal. So let's be patient over here. Since this process might take a while. Again, this thing depends how fast is your computer. Good. We can see this screen, bitstream generation successfully completed. Let's click on cancel. Then over here, click on Open Hardware Manager. And then click here on Open Target and click on Auto Connect to connect to your FPGA. And then after some time, you will see this part over here. This means that we are currently connected to my FPGA. So let's click over here, do the right click, and to upload the code, you need to click on Program Device. After we click on Program Device and we click on Program, the code will be uploaded, and on your oscilloscope, you should see pulse width modulation signals. Next, I will explain an alternative approach for generating pulse width modulation signals. Our constraint file will look the same. Consequently, we don't change the constraint file. We're just going to change the main module. And over here, I'm going to erase everything and I'm going to simply paste the new main module. So let's analyze this new main module. The input and output ports are the same. We have clock and signal. And here's the main difference. Over here, I'm going to generate the value of the pulse width modulation signal and I'm going to store it inside of this register. That is, I'm not going to immediately send the value of the pulse width modulation signal. I will first store it in this register. And over here, I'm declaring the register. I'm calling it as PWM and I'm storing the value of 0. Then here's my period length. This part is the same. Then I have the pulse length and this part is the same. And here's my counter. Counter starts from 0. This always block is triggered on every positive edge of our clock. That is, it's triggered in every clock cycle. And we simply count the counter until we reach the period length. After that, we reset the counter. And this part is the same. However, here is the difference. Over here, in every cycle, that is on every positive edge of the clock, we are going to store the value of the pulse width modulation signal inside of our register. In my opinion, this might lead to a more stable implementation. Okay, so what do? On every positive edge of clock, we trigger this block. Now, if the pulse length is smaller, or actually if the counter is smaller than pulse length, the value of the pulse width modulation signal is high, or it's equal to binary 1. Otherwise, the value of the pulse width modulation signal is 0. That is, if counter exceeds the pulse length, then the value of the pulse width modulation signal is 0. And that's it. And then finally, we simply assign the value of pulse width modulation signal stored in our register to our signal. Now, what is very interesting to observe over here, in between these clock cycles, we will always have the constant value of the pulse width modulation signal, and it will always be stored inside of this register, and this register will be directly connected to our signal. Something similar we did in the previous code, however, we didn't use a register. So let's save this file and let's try to run this file. So how to run this file? Well, again, what we are going to do, over here we need to do several steps. We need to run the synthesis. I will rerun the synthesis and I will click OK. Then after that, we need to run implementation, generate beat stream, and upload the code. So let's do all these steps. Then let's run the implementation over here. Click OK. Now the implementation is running. And let's again be. Next, let's generate the beat stream. And let's wait until the beat stream is being generated such that we can program our device and we can observe the results on our oscilloscope. And finally, beat stream generation successfully completed. Let's click on cancel. Let's click on here, do the right click and click on program device. Click on program and now the code is being uploaded. And again, you should see the pulse width modulation signal with the specified pulse width and the frequency. Okay, that's all for today, and thanks for watching, and see you in the next video tutorial.